The format of e-learning is as follows. Course will consist of modules 5 to 10 minutes each. Modules are related, so it is recommended you follow them in order. A step-by-step guide to build a simple model from start will be given. Models that are pre-constructed are also used to demonstrate certain functions. It is recommended that you first view each module without hands-on. Then repeat the module with hands-on. You can pause, rewind or fast-forward any of the video. Let's go through how ProtaStructure manages the model data and files. ProtaStructure stores all the files of a project in a folder called Project Folder. Project Folder has the same name as the project code, which is the project name. Spaces are not permitted for project code. The project folder is created in a parent folder, called Project Data Folder, which is the parent folder. You can have multiple data folders storing different project folder. Tip: if you are a new user, for simplicity, use just one data folder for all projects. To open a project, the project data folder must be correctly chosen. Click Choose / Create Folder in the Open Project dialog to change the project data folder. This picture on the left shows the Open Project dialog of ProtaStructure. The picture on the right shows Windows Explorer with the project data folder opened. The default project data folder in ProtaStructure is always ProtaData, plus a postfix of release version number. In this parent folder, 2 default Quick Start Guide project folder is created. Notice that the project name is exactly the same as the folder name in Windows Explorer. Do not manually rename the project folder in Windows Explorer. Otherwise, you will not be able to open it, as it will disappear from the Open Project dialog. If you wish to rename the project, please use the Save Project as function in ProtaStructure. Further, do not delete any files inside the project folder. All files are essential to the model. Here are a few recommended good practices managing project files. Always store your project in the local hard drive for best performance. External hard disk and server is not ideal, as files can be very large for large models, as they include analysis, design, reports and drawings. Auto-synchronizing of the project folder with third-party software is not recommended, example Dropbox, OneDrive. Performance may be impacted due to additional memory resources required. Backup your model often manually. Go to File, Save Project as, simply save it as another name. Alternatively, go to File, Archive Project, to create a compact project zip file of the model files only. Automatic backup is also created every hour, which can be restored using Open Previous Backup function in the Building Setout tab. By default, there will be 3 backups, done every hour, which means you can restore previous 3 hours of work. Let us now look at the modeling, analysis, and design flowchart. We first start by building a 3D physical model. It is highly recommended you perform building model check progressively to trap common modeling mistakes as you build the model. As you model beams and slabs, the beam loads are automatically derived using the default yield line or tributary area method. FE load decomposition is the alternative method to yield line slab load calculation. This method derives the beam loads by meshing the slabs in the FE model. This method is able to capture the localized effect of slab openings and concentrated slab loads, such as slab line loads. You can then choose whether to use this method on selected or all beams in selected stories or for the whole model. The general building analysis can be run to generate the column, wall and beam design forces. By default, floor slabs are not meshed in building analysis. There is an option to mesh slabs of all or selected stories. After building analysis is successfully completed, ensure to check and verify the analytical model. You must identify any error or warning messages, such as large deformation or unstable joints. Check also that the deflection and the member forces are reasonable. Check the axial load comparison report to ensure no gravity load is lost, load input equals to load output. After verifying the analytical model is satisfactory, you can proceed to design the beams, columns, walls and foundation elements. There is an alternative to building analysis, which is the FE floor analysis. This method is particularly useful for flat slab where there are no beams to support the slabs. The FE floor analysis can also be used for beam and slab layout where subframe behavior or single-story analysis is preferred. Since analysis is done one floor at a time to accurately accumulate the column and wall loads, a sequential FE floor analysis is required to chase down the loads from top to bottom story. You can then choose to merge or combine the gravity results for column and or beams from the FE floor analysis with the lateral results from building analysis. After merging, the FE floor analysis results will be used in member design. After building the model, we can straightaway design the slab using the tabulated code coefficient or yield line method. Alternatively, for slab design, we can use the same FE floor analysis to generate alternative slab design forces since the slabs are meshed in the finite element model. Slab design can also use results of billeting analysis with story slab included and meshed.
Let us now explore in more detail the different analysis options, namely building analysis and FE floor analysis. This example physical model is a flat slab model supported by columns and lift core wall. Between the lift core wall is a beam. The first analysis method is building analysis without including the slab by meshing. The analytical model is a 3D model of all stories consisting only of frame members, that is, walls, columns and beams. The slabs is excluded. Building analysis is capable of analyzing both gravity and lateral loads as the underlying analytical model includes all elements from top to bottom story. Obviously, this analysis method is wrong for flat slab model, as slab loads cannot be captured by the columns and walls. That is, the flat slab loads will be completely lost. Hence, this analysis method should only be used for beam slab layout, where slabs are completely supported by beams. The next method is building analysis by including the slab meshed. In this case, all the floor slab are meshed. This analytical model is correct and ideal for flat slab system, as the flat slab load can be captured directly by the columns and walls, without having beams. Although this method can also work for beam slab system, analytically, it is bigger and more complex model, hence not that efficient. In addition, the result will not be comparable to traditional method of calculating slab loads on beams first, before analyzing for member loads, due to interference of slab mesh with frame elements. The final method is FE floor analysis. This unique analysis considers only one story at a time. In this subframe analysis, only members and slabs of that particular story is considered and analyzed. As such, in order to accumulate the gravity loads of columns and walls, analysis must start from the top to bottom story separately and in sequence, in process called gravity load chase down. However, this chase down can only provide gravity load result. For lateral load results must be obtained from building analysis. Hence, the need to run building analysis first, before performing FE floor analysis. Generally, FE floor analysis method is more complicated and longer and is usually used for specific reason where subframe analysis is required or preferred. For example, FE floor analysis may be useful to analyze and design slabs by meshing of one particular story, as slab design is usually designed only to gravity loads. Overall, we recommend you always use building analysis method as the first preference, as it analyzes gravity and lateral loads using a single consistent analytical model.